Hi guys, you all know me now. My name's Mike Shoresman. I'm with A.O. Reed. Today's March 15th, 2016. We're going to be training on Phoenix valves today. I'll introduce you Rich Yardley with Nematic Engineering, and he'll go over a slideshow real quick, and then we'll walk out in the field and see the location of these valves. All right?
You good?
That was awesome. I don't think I can do that good. My name is Rich Yardley. I'm with Nematic Engineering, and I'm here with George Medina.
Pleasure.
And Don Tilsky. And George was project manager on this project. Don did the startup on the project and commissioning. And I stand up and talk in front of cameras. So that's how we divide responsibilities in our company. My slide advancer is working. Awesome. Nematic Engineering, our business is basically PhoenixControls. So I'm going to talk about various things. I'll whip through slides real fast. You want me to slow down, I'll slow down. You want me to speed up, I'll speed up. You want me to sing and dance, you'll be sorry, but I'll comply with your wishes. So, Nematic Engineering's been around since 2000. I've been working on the campus since about 1988. So, we got a lot of Phoenix valves all over the campus. The implementation at Altman is different than some of the other buildings. So I'm going to kind of hit on that, but I will talk about the Phoenix valve and how it works. And we specialize in critical airflow applications like this. So we do these kind of labs. We got mainly in this building we're doing the vivarium. So we got about 30 other valves in the building, but most of the valves on this project are down lower level 3 west side in the vivarium. So that's where they are in this building. We do a lot of cool stuff, and we're a really good company. Details furnished upon request. You'll be the judge of that, I guess. We pay a lot of attention to design and stuff like that. It's really important to us that your buildings work well, and so we need your feedback as well. If you don't like something we're doing, let us know. We'll do it different. We'll do it better. But our goal is to give you the best possible building, not only from a design standpoint, but even operationally. We're working with the energy manager on campus. Maybe she's not. Maybe John is still the energy manager. But anyway, we're working with Anna to try to get in a program where we go through the buildings on a regular basis to get them all brought to the highest level of operating efficiency and of course, great process control. So what we do is precision airflow. With precision airflow, you want to optimize efficiency. You don't want to use any more energy than you have to. You gotta have great process control. The way these buildings are designed that Phoenix is used in, they're almost inherently inefficient because process control is so crucial. That's why your air handler almost always delivers 55-degree air, and then in the lab building, you reheat it at the zone level, most of it at the zone level. So you think, oh my gosh, you're cooling it so you can heat it again. Let's drive to work with the gas pedal all the way on the floor and modulate the brake pedal on the way to work. It's kind of the way the buildings run. The reason you do that is because you need really good temperature control. If the air, you say, oh, I'll take my discharge air, I'll bring it up to 65, just, supply air temperature reset. You can do that, but then you got a couple zones that need every drop of that 55-degree air, and now you start losing control of your zones. So you design with a lot of cold air, most of which is reheated. By putting in Phoenix, you can vary the volume. You can reduce the volume of air. Now you're reducing both the cooling and the heating and the fan power, and everybody wins. So what our goal is to make the system as efficient as possible, to optimize efficiency. In a vivarium, it's so critical. These vivariums are designed to be two-state. Basically, the rooms are operating constant volume most of the time, and then there's a switchable mode. So let's say the room is slightly positive because you got some immune compromised critters in the room, and then there's an outbreak, so they want to flip it to negative. So you flip a switch, that's the two-state. We would flip to negative. When we flip to negative in the room, we would tell our corridor to give a little more supply air in order to balance the floor plate. So that's basically, Don, correct me if I'm wrong, that's basically the sequence we're talking about here. Most of the rooms operate constant, several of them are switchable. The switchable is for an and I've talked to a lot of veterinary medicine guys, and with veterinary medicine, I asked them, what's the likelihood of having an outbreak in your facility? And the doctors say Well, what do you mean? I said, well, what's the chance that there will be an outbreak in your vivarium? He said, oh, it's 100%. We'll have a lot of outbreaks in the life of our vivarium. It's expected. Not hoped for, but it's expected. So then the question is, how do you respond to it? You do everything you can with your procedures. But when there is an outbreak, you want to make sure that the room gets quarantined, isolated from the rest of the vivarium so it doesn't spread. So that's basically what's going on with the Phoenix valves in this. Anyway, the purpose of the system in general: operate efficiency, reduce operating costs as much as possible, give you the best process control. These animals, vivarium, you just can't be down. Downtime isn't allowed. They need their air all the time. I'm talking about now lower level 3 west, so in the vivarium level, that's what we're talking about. You've got to have excellent process control at all times, and you can't be uncomfortable. Even you look at the way a vivarium room is designed, the holding rooms, the room itself, they call the macro environment when you get into veterinary stuff a lot. The macro environment, and then they put them in these little cages, micro-isolator cages, and that's called the micro environment. So the principle is you deliver air comfortably into the macro environment, and then there's fans on top of the cages that deliver it into the micro environment. That way, if you have some problem with your central systems and the air starts going a little bit wonky, you can open the door to the door. That was pretty cool. Open the door to the corridor, or the corridor to the door, whatever you want. You open the door and try to keep the macro environment kind of balanced so that you don't destroy the animals with really hot or really cold air. Anyway, give great process control, and our goal is always to give you the best value. Okay, value is, that's a talk I give to some people. No, where do we do it? Phoenix does wet chemistry labs, life science labs, and vivariums. Again, here is mostly vivarium. Other than the vivarium, you have some fume hoods, but the fume hoods are all constant volume fume hoods. But if it goes into alarm, you're going to have to know how to work on it. We'll talk about that as well. So the main place where we have them in the life science area of the building is on fume hoods. We also have some point exhausts and other things in there. But again, mostly the vivarium, fume hoods, and some point exhausts. There is no wet chemistry in the Alton facility. I want to talk about the valve. This is what a cutaway of a Phoenix valve looks like. I don't know if you've seen it before, but the air enters on the left, goes through the valve around this kind of hemispherical cone, through the throat of this venturi, and out that way. If this were a supply valve, the fan would be on this side, pushing air through our valve. If this were an exhaust valve, the fan would be on the right side, sucking air through our valve. But the physics, the operation of the valve is the same either way. So it was designed originally for wet chemistry labs. And it's not a cheap thing, but because it was so expensive, people weren't using it so much for life science vivarium. So we re-engineered it for biotech, for vivariums, hospitals, things like that. So that reduced cost. The valves we have in this building are called our Traxel valves. They're about 40 cents on the dollar compared to our wet chemistry valves. So they are competitive with a VAV box, only it's a much better device for you to work with. We have reduced pressure drop requirements, and we talk BACnet, which is really cool. So our system, I don't think the entire building's tied into BACnet. I could be wrong. Or is the whole building tied into BACnet, or just the vivarium?
For the Phoenix BACnet?
Yeah.
Just the vivarium.
Okay. So the vivarium is tied into the Johnson system, so you can see all kinds of information there. Anywhere where you use Phoenix, directional airflow matters. That means the positive room should stay positive, the negative room should stay negative, something like that's going on. If you don't care whether the door is blowing or sucking, you don't need Phoenix, just go with a VAV box, But the fact that you're using it here means the directional airflow does matter. And in a vivarium, it's really important that you maintain proper pressurization. If you've got these animals, which these transgenic mice could be worth $100,000 each, so you got all these little critters in these little boxes, you better not muck up. So we keep the positive room positive if they're immune compromised, so we don't bring anything bad through the doorway. If they do have some sort of outbreak, we can pull the room negative so that you maintain the space pressure in that case. Wet chem we don't have here. Really what we're talking about is pressurization control in the room. Also, in a vivarium, when you're pulling it out of the room, sometimes we pull the exhaust directly from the cages, and sometimes there's a fan involved. Do you know whether cage racks have exhaust fans on them or not?
I haven't seen any of the cage racks yet.
We'll find out on the job lot. If you have an exhaust fan that's got a HEPA filter, you're probably okay from a dander standpoint. If it doesn't, it'll really load up. Our valve is fine with dander. It resists it real fine. There's really nothing else in the industry that can. So either way, you're fine. The basic principle is we put our supply valve. This is in the vivarium. We do supply and exhaust. In the rest of the building, we're only on the exhaust side. In most buildings on campus, we do supply and exhaust. Supply air comes in through one of our valves. Supply air goes out through one of our valves. Our valves are very accurate at knowing how much air is going through them. So if this guy says he's 400, he's going to be within 5% of that. He could be as low as 380 or as high as 420, but he's going to be about 400. And if this guy says 500, he's going to be within 5% also. He may be 475 or 525, but he'll be somewhere in that window. So we know that the goes into is less than the goes out, which means you're going to have air come in from the corridor to the room. And that's the basic principle behind the Phoenix system. And it's really the only way to control pressure in a vivarium properly. Some people try to measure the pressure of the room, but you really run into problems because when you open the door, the system doesn't know what's going on. If you have a 20 square foot opening here and you pop that open, the relative pressure between these two spaces will be, let's see, 0. It will literally be 0.00000, and I'm getting tired. You know, it's beneath a measurable value when you open the door. What will happen when you close the door, you will achieve some pressure differential. Their vivariums are very tight spaces. You got hard lids and gasketed access doors, and so it's going to be a tight space. So you will get a pressure relationship between these two, between the corridor, which is typically out here, and your holding rooms or procedure rooms, whatever they are, when the door is closed. And that's, you balance to that, and that's what your balancer did on this job. Who balanced this job, you know?
Balance America.
What's that, Balance America?
Balance America.
Okay, good, there you guys. So the balancer room they're going to hold, they might make this room minus 0.03 or something like that. Whatever they went for, we're going to hold that pressure when the door is closed. When you open it, it's going to fall off the table. You're not going to have any measurable amount. So you try to control based on that pressure. It goes crazy every time the door is open. Or you lock it out when the door is open, then they prop the door and you really don't know what's going on. So really the best way to do it is to accurately measure the supply and exhaust, know the difference, and make sure that the delta comes in through the door. Direct pressure really only works if you have an airlock, some kind of architectural barrier between the space you're trying to control and the neighboring space, so you never pop the bubble. Again, we keep the good stuff in the good area and the bad stuff in the bad area. This doesn't really apply to what we're doing, but I always like the cartoon from the New Yorker. Where, you know, basically, if you're working with nasty stuff, you want to make sure you're safe from where the nasty stuff is. This doesn't really have anything to do with airflow, but I thought it was a funny idea, so that's the end of that slide. Okay. So what Phoenix does, it controls airflow in a completely different way from the way everyone else does. With a VAV box, it's measuring air pressure. And it says, okay, I think that's 800 CFM or whatever it is. It measures the velocity pressure of the air you can't really measure the velocity pressure because the static pressure, the bloom pressure is built into that number. So it measures total pressure, static pressure, takes a differential and gives you velocity pressure. So a VAV box, you're kind of measuring the flow. We don't measure the flow, we meter the flow. What? You don't measure flow? What? And it actually ends up being better in this application. So if you're used to working on a VAV box, this thing works in a different way. Flow measuring has a limited range of operation because the velocity pressure varies as the square of the velocity, which is to say when your velocity drops in half, the signal you're measuring drops to 25%. When your velocity drops to a quarter, the velocity pressure drops to 1/16. So you're down in the, super low range. You're like trying to measure 6%, you probably got a 1% error on your transducer. So VAV boxes really start messing up if you try to control them with any kind of turn down. Someone from Oceanside wants to say hi. And flow measuring, you got to have what's called fully developed flow. You got to have long duct runs. Well, you don't often get that. In fact, you'll find in your vivarium, you got a lot of vertical up and down valves where you're just kind of dropping down into the vivarium and pulling up out of the vivarium, and you don't have a whole lot of real estate to work with in terms of developing your airflow. And flow measuring can be messed up by dander, for example, on the exhaust side. Phoenix valve doesn't have a problem with any of these things. And there's time lags which don't apply, that's wet temp thing. So flow metering is better when it's done right, and Phoenix does it right. The first thing we do is we decouple pressure independence from flow control. Blah, 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 what does that even mean? I'm going to get into it in the next slide. So, but by separating them from each other, you really get tremendous stability. And also, a Phoenix valve can't be fooled by a bad inlet condition. A VAV box, if you give it a bad inlet condition, it doesn't know what to do with it. And it allows us to feed forward. Phoenix valve, we're driving to position so we can get to where we want to very quickly and very stably. In a normal control system, when you're trying to achieve a set point, if you go too fast, your set point might be here. So if you're going too fast, you might overshoot, and then you go, oh shoot, we're too strong, we're not strong enough, and you can set up some oscillations. Sometimes you'll see boxes oscillating around. You slow it down, and then when you get to the right speed, you can be stable. So you shoot for stability. The Phoenix valve gives you this is what's called critically damped control. It responds quickly and stably to where you need to be, and you're not going to get any hunting around. I know we have one actuator out there that's kind of wonky right now, but we're going to replace it. It's a bad actuator. It's not the Phoenix.
In this building?
In this building.
Oh, okay.
The one we looked at yesterday.
Don's going to do it.
Oh, yeah.
Yeah, that's just a bad actuator. That's just a crummy actuator. Sorry. We try not to give you crummy actuators. Our goal is to give you quality actuators, but sometimes
I hear you.
sometimes a bad one slips through.
They're, for the most part, they always are.
They're good reliable devices.
Yep.
So again, here's a kind of a cutaway view of the valve. Air enters from the right and goes to the left through the valve. And this one, does that look like 500 CFM? 1, 2, 3, 4. Okay, so each one of those would be 125. Okay, that's not supposed to be that way. Anyway, air just flows through the valve. And we got this cone attached to this shaft with some springs. And those springs, you don't see any of this, that's all inside the valve. But so it's constantly adjusting here. As pressure changes occur in your system, this cone instantaneously repositions to keep your flow constant. So bad inlet condition, all kinds of other stuff, no problem. It'll fight it off bravely. So basically we're going to tell you, we're going to set this shaft to a position, and that's the 500 CFM position, and we're good to go. And you say, wait a minute, but what if the pressure changes? Those remote devices, you set the damper, and then the pressure changes, and you got to kind of adjust your damper to try to keep it at 500. All that adjustment is happening in here with this cone and spring assembly. Big principle of how the Phoenix valve works. Internal, mechanical, system-powered pressure independence. Doesn't always make sense right to begin with, but it'll make more sense as you work with it. Every VAV valve we make is characterized on a flow station. This is a sample of one of our 12-inch valves. We measure the flow at 48 different points as we move the shaft of the valve. So on the previous slide, we move this shaft, so we move the cone in and out, and at each one of those 48 positions, we take a measurement to see what the flow actually is. We also take multiple pressure readings for most of these settings. So we actually take over 120 different readings for every valve we make. We didn't just do it once, we don't just do it occasionally. Every VAV valve we make gets put on a flow curve like this. So for a given shaft position, you have the corresponding flow. This shaft position would give you 793 CFM. So when we move our valve, we're going to move it to a position, and we know precisely where that position is through a rotary potentiometer, and that will give you that flow. And we've characterized the valve at the factory, so we know that position is that flow. The only reason that position wouldn't give you that flow is if your fan is off or underperforming, and we have a way to correct for that on this job as well. All right, so for flow control, we just move our shaft. You move the shaft, you get more air, the arrow gets bigger. You get more air through the valve. Move the shaft this way, you get more air. Move the shaft that way, you get less air. Pretty simple the way it works. The pressure independence, we got a little movie here. I think the sound may work in this room. So it's going to show you how the pressure independence works. The following.
To demonstrate the complete inlet and exit insensitivity of the Excel valve, we have connected a clear cutaway version to our test station. The valve has been commanded to a 500 CFM flow set point. The screen inset shows the actual flow and static pressure in the duct as measured by the test station.
Measured flow.
First, we bend the ductwork to a 45-degree angle. Next, the duct is bent further to a tight 90-degree angle. As you can see, the measured flow remains virtually constant at 500 CFM. Although not necessarily seen in the field, this tight 180-degree bend definitely shows the valve's complete inlet insensitivity, as does the following tight S-bend. Even this unlikely arch bend does not affect the flow through the valve.
Still constant 500.
Notice that when the flex duct is pinched and severely restricted, and even when part of the duct itself is pushed inside the valve, simulating blockage caused, for example, by lab tissue or a loaded HEPA filter, the flow still remains unchanged.
The point is, in operation, you can throw a lot of curveballs at this thing and it will continue to flow its measured, characterized flow. When we say we're going to give you 500, you throw a bunch of curveballs at it, it's still going to give you that 500. I said the only reason it wouldn't is if your fan drops off or a fire damper shuts or something like that. So for that, on this job, we put pressure switches across our valve on the critical valves, and Johnson's monitoring that. So if you have a low pressure drop on any valve, the Johnson system will alarm. Won't necessarily tell you why it's alarming, but it'll say, hey, we got low pressure on this valve. On the supply side, it could be that a fire damper shut. On the exhaust side, it could be, I've seen fan wheels load up with dander where they can't perform anymore. So it could be any number of different, it could be a broken belt, who knows what, a tripped VFD, I don't know what it is, but whatever it is, if you get low pressure on the critical valves in this building, you're going to get an alarm at the front end. So I want to talk a little bit more about some of the unique features of the valve, not to put you to sleep, but sometimes it has that effect. The accuracy of the valve is plus or minus 5% of signal. People say, well, I've got a 1% transducer. Yeah, but your 1% transducer, when you use it down at the lower 25%, has an inherent 20% error to it. So it's 5% of signal. You really we're always within 5%. Whatever we're working for, we're within 5%. High turn down, that means controllable maximum to controllable minimum. We have at least 10 to 1. Not a lot of turn down on this project. It's an important feature of the valve, not on this job. Those are easier words to say, simple and highly reliable, but it really is. Fred Yeager over in FD&C was looking at an alternative product. And he was considering it pretty seriously. And then he had two of them on the table side by side. I said, have you ever looked at two valves side by side? He said, yeah. I just asked the question. He goes, the Phoenix valve is built like a tank and never has problems. The other one, I could see that going bad real fast. So it really, hopefully this is the last you'll have to hear about the Phoenix system, except, boy, the Phoenix system's working great. It really is a simple device and really, really reliable, with an occasional bad actuator during startup. Insensitive to inlet and exit conditions. You can come into it with all kinds of, you got bad inlet and outlet conditions on this job due to the valves being all in vertical and the interstitial above the vivarium. The majority of the vivarium valves are there. No problem for this valve. Factory characterized. There's no such thing as an NIST certified valve, but NIST, National Institute of Standards and Testing, has a program called NVLAP, National Voluntary Lab Accreditation Process. And NVLAP does accredit your valves. So our valves are NVLAP accredited, which means they're designed and built to NIST standards and tested to those standards. Every claim we make has been tested by the National Institute of Standard and Testing's Voluntary Lab Accreditation Process. Anti-fouling, and when you're measuring, this is what you have in front of a VAV box. When you're measuring, and we're on the medical campus, this was a VAV box in a hospital exhaust or return, I can't remember. 6 months later, they took a picture of that same device and it looks like that. So when you're measuring, the measuring can be fouled up. This happened to be lint, but in a vivarium, dander from the animals will do the same thing. It can really foul up your sensor. Your sensor stops reading back. We did a job for City of Hope where they were measuring to verify the Phoenix valves. They put in flow measuring stations, real good ones, air monitor, real high quality air monitoring stations. But on the exhaust side, they got the lint in them. And after 6 months, they called us with a 5-alarm fire. Every one of our rooms, which is supposed to be negative, they're all isolation rooms. They've all gone positive. There was a whole floor of them. I mean, it was a big deal. So we went to the rooms and we said, by the way, every one of these rooms is still every bit as negative, but the front end with their air monitoring stations was reporting the room as positive because they were no longer measuring the exhaust that was actually there. So measuring has problems. Phoenix valve meters, it doesn't measure. We're going to continue to give you good control even if you get stuff like that going on. There is no required maintenance on this stuff. I mean, we like any system you want to look over from time to time, but there's no no transducers to zeros to span, no fittings to grease, nothing. They just set them and forget them. No ongoing calibration, and we think it does give you the lowest overall cost. So, I don't know. That's basically what it is. It's not just, okay, VAV boxes don't work very well. You got a cancer center, I don't have to tell you that. So when you track VAV boxes, you run into some problems. And just one example, we did a large hospital further south in San Diego, not owned and operated by UC San Diego. And we had a flow measuring station, but it was in a bad location. And when we were flowing 40,000, a big built up system, when we were flowing 40,000, sometimes the station would measure 40, sometimes it would measure 20, and sometimes it would measure 70. I mean, depending on whether you came up at it or down at it or whatever. So some people say, well, I'll just put a K factor on my box. Well, there's not always a K factor you can use. Sometimes the air flows both directions, and then you really run into problems. So you don't have to worry about that with Phoenix. Okay, we do tracking control. I don't know, just in terms of the way the building works, right now you've probably got your static pressure set point 2/3 of the way down your branches, something like that. One thing we sometimes recommend is maybe measuring out here, and if you don't want to have too much, if you have plenty out here, as it moves around, you can reset your static set point based on some settings out at the fingertips. With not being done on this building, probably not needed for a vivarium, but some of your science buildings, it's something you could look at. So another point, when they say how much energy does the Phoenix valve use, you can't just measure here and say it's using more energy, because when you turn down a little bit of airflow in here, your exhaust fan will slow down, your supply fan will slow down, your chiller will slow down, your cooling tower will slow down, your condenser water pumps and chilled water pumps will slow down, your boiler and heating hot water pump will slow down and use less reheat. So it's hard to say where the energy comes from, but suffice to say there's just a whole lot of energy involved with every drop of air you put in the building. So every bit we can save has a big consequence. We don't need to go through this. Airflow saves more than fan horsepower. Now, that was, I just saved you a whole lot of engineering. I do talks for different reasons, and anyway. Commissioning is uneventful. You can tell me we just finished commissioning. Heck, you sat out of the last commissioning meeting, there was nothing to do, which was concurrent with this meeting. So, good advice. I think that's pretty much all I wanted to say. I don't know if you have questions or if you want to. We can talk a great deal. I think the best thing might be just to go out there, go through, look at a few of the rooms, look at a few of the valves. We got fume hood monitors out there. If the fume hood monitor alarms, you're going to want to know that. And just so you know, our fume hood monitor has 2 different audible and visual alarms to it. So by listening or looking at the alarm, you can tell what the source of the problem is. So that's kind of important to know. If it beeps and flashes fast, beep, 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 get that there? Just trying to make sure it's then the problem is low pressure drop. There's not enough suction. Somehow the hood isn't feeling enough suction. If it's a slower beep, 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 that means someone has probably raised the sash The hood's only designed to an 18-inch operating height. That's where the sash stop is. If someone defeats that sash stop and takes the sash higher, you're going to get the slower beep. Unless you also lose fan at the same time. The low fan alarm overrides all alarms, so the fast beeping will trump all others. If you have a fast beep, you might also have a slow beep, but there's no way to know it unless you fix your fan problem. Like the screen with the button. I think that's it. Again, I think we should probably look at one fume hood. There is one fume hood in the Bavarian, but we can look at a fume hood somewhere we have them on level 1 and lower levels 1 and 2. Before I forget, I brought 2 O&Ms today. We have 3 flavors of O&M at Nematic Engineering. There's the contractual obligation O&M that we turn in the day the job starts, which has no useful information because the job hasn't been built yet. This is the O&M that we figure we can get in your hands, so this one actually may get used. We put everything in here, even though there's still some warts. We have a few, valve was fluctuating. We're going to have some notes in here. You're going to say, hey, everything doesn't look perfect here. That's because the job is not completely finished yet. But the O&M is divided into a few sections. At the beginning is what we call a room schedule sheet that lists, in order of room number, every valve we have on the job. How much airflow it's doing at min and max, what the size of the valve is, what the function is of the supply, exhaust, fume hood, whatever. So we have 7 pages or 8 pages of valves, fume hood monitors, and other things in here. The next is the sequence of operations that tells you how the system is expected to operate. If you expect it to operate differently, this is how we designed them to operate. So if you want them to operate differently, we can do other sequences, but these are the sequences that we designed for this building. The third section is product data sheets, and it includes instructions on how to calibrate our monitor. It's 100 pages of stuff, a lot of which has lines through it that doesn't apply to this job. Fourth section might be the most useful, and that's what we call our startup sheets. And I'm going to go, and this is 130 pages of startup sheets. We do very thorough startups. I'll pick a room here as an example. I haven't looked ahead, but this is room L3 West 334, and it's called SW2. But you've got kind of design CFMs there, and we're checking different performance. So the occupied heating, unoccupied, and occupied cooling. The flows are the same for all 3. We got supply and exhaust, and the rooms are supposed to be, by design, about 108 CFM positive. We measured them at 105 CFM positive. The previous room, shown here, is called SW1. So these 2 are the same room, but this is in state 2 and this is state 1. So in state 1, the rooms are 95 CFM negative. In state 2, the rooms are 105 CFM positive. That's just showing you. So and there are room number here. So if you're in L3 W334, in switch position 1, the rooms are negative by 100 about, and in switch position 2, same room, the room is positive by 100 CFM. And this, when you see the software numbers filled out, that means Don's been in and checked out the room.
Okay.
So, and notes, switchable room by JCI, okay? So how's it switched? When do you switch it? Why do you switch it? Okay, JCI is controlling the sequences here. We're merely responding to their input. So when it switches, we'll go from negative to positive. When, why, and how's it switched? Talk to Johnson. And we've rung out the whole switching process. I mean, they send a switch via BACnet to our system, and so we've checked that out. We've rung that whole part out with Johnson.
Yeah, the balancers actually, when they did the balancing, they had Johnson switch it to do their test.
So we didn't do an artificial switch just by putting a jumper in on our controller. We actually had to go through the Johnson system. So it's been rung out all the way through. So the startup sheets tell you every room we've been to, what we measured, what we found in every room. The final tab is wiring diagrams. So if you want to know why something's wired some way, or how it's supposed to be wired, doesn't look right, we indicate also on here switches where Johnson put pressure switches in. So if this was deemed to be a critical valve, Johnson is measuring that pressure
Okay.
at the front end.
All right. Nice.
That's it. That's the O&M. We got 2 O&Ms for you. And then I have one here has some markups on it for our internal use.
Make sure these are in the operator workstation room.
If somebody
and
has that,
back at the shop.
yeah, and we can, we keep all this stuff, soft copies and hard copies and stuff, so if you need it, we can get it to you, but we want you to have some idea. That's the inventory of what we've thrown into this building.
All right.
If I was you, I'd want to know that.
Oh yeah. Oh yeah.
That's our owner's manual for our system, so.
Is there another one of those for Reed?
Yeah, we've turned that in. We prepared that for Reed. We gave them a soft copy.
Okay.
So them, you, I don't know.
Because at that point it'll be turned over to the general contractor, and then we'll turn it over officially to UCSD as well.
Correct.
So.
I call this the bootleg copy.
Sure.
Because knowing the way formal channels go, sometimes it just never makes it there. So ideally, you'll get a perfected one through the channels. If you don't, you have at least something you can limp along with. Sure.
Any questions for up here in the building? If not, we'll go down the building. You guys good?
I'm good. I'm ready to go.
Okay.
With the fume hood, you want to be able to raise the sash, and it hits this sash stop at 18 inches. The light should be green all the time. So you raise and lower the sash, the user's using it, they have 100 foot per minute capture velocity. If you have a meter, you could measure that. Are there any Kim wipes in this lab?
Not yet.
Not yet. There's these Kim wipe tissues that the researchers use. If you hold it up to the sash like this, it should go in at about a 40-degree angle. So paper's too stiff.
Okay.
So the Kim wipe tissues are a little floppy. They go in at about 40 degrees. You can't feel 100 feet per minute. So you get your finger wet. You can't. The proper capture velocity you can't feel here. But you got a green light. You can put your tissue in. You can say, good, it's flowing. It's doing what it should be doing. You can raise and lower the sash. The flow is not changing when you raise and lower the sash. It's got a bypass up here. So when you lower the sash, air comes in over the top here into the hood. Oh, that's pretty good. That's a wet wipe, but it's pretty close.
Yeah,
That's a little bit. So that's about right. Yeah, it's about a 40-degree angle. And they look just like this. The Kim wipes do. They don't clean your hands. But yeah, and that's not. Maybe that's only about a 35-degree angle. So Kim wipe's a little bit lighter. It's not wet, but it goes in at about a 40-degree angle. And so when you open the sash, you want to see about a 40-degree angle going in, and you know the hood's operating right. I trust that more than any monitor on any side. The guy said, I'm sucking fumes. Well, you put your thing here. There's things they can do. If they put equipment right in front and don't put it up on blocks, it'll block the airflow and you'll get dead zones. So there's things they can do in the operation of the hood that can make it work. But in terms of the mechanical system, if it's pulling in at a 40-degree angle, you say, hey, that hood's doing what it should be doing. Notice the green light here stays on all the time. You raise and lower the sash. Again, when the sash is up, the air goes here. When the sash is down, the air comes over the top. The flow of the air never changes. The hood is only designed to get you to here. We have attached to this hood, not really very visible, a vertical sash sensing cable. I'm going to pull it out there. You see that cable there? That's our sash sensor cable. That's attached to the grab hold at the bottom of this sash, and it's mounted up here. That's measuring the sash height. We can only capture, there's only enough airflow designed in to get you to this sash stop. So if someone reaches in and defeats the sash stop and takes this higher, the hood will go into alarm. Notice that's the slow alarm. So someone says, hey, my hood's alarming. You raised your sash too high. You're only supposed to, this is for setup. You can mute that audibly, but the red light will stay on. During setup, you can work with it up here. But when you're ready to do your science, bring it back down, get back into the green zone. So if someone calls with an alarm, one possibility is they've raised their sash above the sash stop. All they got to do is lower it back to the zone where it was designed to be operated, and it'll go out of alarm. The second alarm is called an emergency exhaust button. You push that, and it will also beep. You release it. What does that button do? Absolutely nothing. On a VAV hood, it would do something. We keep it on this hood, but it doesn't do anything other than beep and cause a red light. So if someone pushes the emergency, they may say, my hood's an alarm. It's push to set, push to release. There, you're a hero. On a VAV system, what that will do is bring you full flow regardless of sash position.
Increase the flow?
Increase. It'll increase it to maximum, but this is already set up at a constant volume where they want it to be, so that doesn't change anything on a constant volume hood. We didn't want to build 2 monitors, so we just built one. So again, if they defeat the sash stop or if they push that button, you'll get a red light and a slow beep. If you lose your fan, it will beep a lot faster. And I don't really want to simulate that. It would be troublesome. We could get a ladder and pull a port off our pressure switch, I guess. But anyway, it'll beep faster. You hear it faster. So you hear a slow beep like that, you either push this one button or lower that sash. An alternative thing is this sash sensor is attached to this sash. If that somehow comes disconnected, it'll retract all the way back in and it'll perceive the sash is too far open. That's a third possibility. So if you come out and you have a slow beep, make sure that button's not pushed. Make sure the sash is below the sash stop. If neither of those stops the slow beep, probably this cable came disconnected. Make sense? Yeah, go ahead.
Is there any variable air volume of fume hoods in the building?
Not in this building.
None at all.
None at all.
And the chemicals that they're going to be using are going to be just fine, and
Yep.
not going to be using any of that nasty stuff.
It's not a heavy chemical use lab, and these hoods capture just great. A constant volume hood captures well, almost as well as a VAV hood. They're both excellent capture hoods, so you won't have any problems with that. Notice we do have a couple loops here where we connect our sash sensor to an extension cable in order to get all the way down there. You can see a couple loops there. That is the thing, that knuckle there sometimes catches on. Don and his team pay real good attention to making sure that that doesn't catch on stuff going up and down, but sometimes it may catch on a piece of the infrastructure up here, and that's when this thing might come disconnected. That's pretty much it on fume hoods, unless there's other questions.
All right. My name is Don Tilsky. I'm with Nematic Engineering, and we're just going to kind of talk about the valves that we have in the vivarium interstitial catwalk area. We have 3 different types of our valves here, the ones that Rich was pointing out. We have a general exhaust valve that is just basically, it looks like the spun aluminum valve itself. These down here, they have a pressure switch where a port that we have a polytubing, pneumatic polytubing on either side of the valve. That's what basically tells the valve if it has the correct differential pressure across it. If the fans drop off, there's a little dry contact switch in here that the exhaust or supply air, as long as it's within the specifications that it needs to be, it holds that switch open. When the fans shut down, it closes and it sends a signal through these wires into our board, which in this building here, these are tied directly to Johnson Controls front end, so they should see an alarm or something to pop up there, probably going to you guys. This is just a regular general exhaust valve. We also have our coated valves that are more for like the hood applications or biosafety cabinets. Whenever you put any type of chemicals in there, you want this coating on here that's going to kind of protect the valve and not be so corrosive. It also has the pressure switch. It has its own controller board on it. It's receiving signals or whatever we program it to be. If it's a constant volume, we directly put the values in there. And then the third valve that we have, this is our supply valve. You can tell it's a supply valve because it has this black foam insulation on it. That's usually how you can kind of tell the differences in our valves, if it's general exhaust, hood, or supply. And in this building application also, it has a pressure switch. Because it's a vivarium system, they want to know, and you're basically monitoring pressures in there, so you need to know if your supply fan has enough static pressure, if your general exhaust has enough static pressure, and if the hoods have enough static pressure. These corridors, some of these corridors, these are the ones that we were talking about that are maintaining the switch through Johnson Controls. When I believe the biosafety hood valves, when the switch is made from one way or the other, the biosafety valves stay constant because it's actually connected to a biosafety hood cabinet, so that will never change. What's going to make the change is the difference between the supply valve and your general exhaust valve. When we get that signal, we're going to tell the supply valve to go from either 500 supply, 600 exhaust, to maybe keep exhaust the same and make the supply 100 more to make it a positive, or negative, vice versa, whatever it is. It's in the startup sheets as to which way the room goes, when it gets the signal, which valve actually moves. In some cases, both supply and general exhaust move. Most of the cases, just one valve will move. And it's some of them, it's the general exhaust that moves up and down, the supply stays the same. Some cases, it's the general exhaust stays the same with the hood valve and the supply valve opens and closes. And again, the corridor valve, it responds to those switches also. It takes a total of all the feedbacks that we've programmed in, and it, if you have so many rooms that basically are positive and so many that are negative, it's taking that math and it's doing its, we've programmed the actual formulas in there to make sure that the supply and the exhaust for the corridor is maintaining what it needs to do for whatever polarity the room is doing. I think that's pretty much all we needed to see down here, unless there's any questions about the way things are running here, or if you have any questions about.
Well, maybe you should go through the various components on the valve. You put in your pressure switch, maybe the control board, take the cover off, an actuator, just so you know what it's a V-pod.
Okay. So I'm going to go ahead and take off the controller cover here. So we have a backnet controller board. It's supplied with 24 volts VA AC. So the pressure switch is a dry contact with the air coming through here. When it gets closed, these two connectors are run through an orange wire. Actually, on this system, like I said earlier, it's running straight to Johnson Controls. It doesn't even land on our board. When there's a fume hood landed on it, like the ones where the fume hoods are, our pressure switch has to be landed on this board. We'll get the alarm comes through here. Actually, it doesn't really need to be landed to the board unless we're really talking to your front end and we're supplying all of your front end system. But I think in this building still, we have the pressure switches going directly to JCI, I believe, right?
Right. The difference is, you say on a fume hood, the pressure switch has to come to the monitor.
It goes directly to the monitor.
And from the monitor, we have
Right.
direct contact.
So a fume hood application is slightly different. You would actually see it at the fume hood monitor. And then we have a Johnson Controls 2-conductor. There's an actual alarm, normally open or normally closed contact alarm in the fume hood monitor that we're able to send that same signal to the front end. You basically just have your regular comm. It's MSTP comm. I believe there's a switch. You just have your voltage potentiometer is inside underneath this cover. That's the potentiometer that's connected to the pivot arm of the valve. So as that turns, it changes the resistance in the voltage. The resistance in the voltage on the board tells the board what flow feedback it has, and it's basically coming through a couple wires that are on here. Your basic wires are just your power. On this one, it's an exhaust only card, so there's no tracking valve. This is technically usually a tracking valve, but it has its own controller on it for the application of this building. So it has its own actuator wires. That's this 3-conductor that goes from here to this controller, the actuator controller that tells it to open and close. You have your comm, 2-conductor comm wire ran here, and power. And that's pretty much it. Normally, if we need to receive a local flow command, that would be a wire coming in. It's all programmable. They can be changed through jumper settings if it's going to take a 0 to 10, 0 to 5 volt signal, or dry contact. That all can be changed out with jumpers. I think that's pretty much it for that one, man. Unless there's any other questions.
It's 24 volt. It's 24 volts, right?
Mm-hmm.
Is that who provided that? Do you know? Is it from JCI?
I believe on this building we provided the transformers for the PhoenixControls here.
Where are the transformers?
Yeah, they're all right along the walls here. We can go take a look at some of those. Okay, so as we were talking about earlier, the valves run off of 24 volts AC signal. If you ever go up to a valve, you take the cover off and you see that there's no lights flashing. There should always be at least one light blinking. If there's no lights present in there, the first thing you might want to do is come to the transformer panels, and you want to just make sure that if there's a 2-conductor wire landed to it, I think I can bring that in there. You have all these wires, and I believe they're all labeled to what they go to. If any of these is off, they all have their own individual. This is a 500 VA total transformer with 5 individual 100 VA circuits. Sometimes if something happens and a wire gets nicked and it gets shorted out, it'll trip at this circuit right here. All you have to do is if the red light is off, you turn it off first, and then you should be able to just push that and reset it and then turn it back on. If it trips again right away, then you have a problem somewhere in the wire. You just got to go find out. It could be that somebody put the cover on and it sheared the jacketing on the wire to where it creates a ground in it. But that's where I would start if you don't have any lights on your controller when you first go to it. All right, so as we were discussing earlier, you have some of your corridors where we have programs and code written in to maintain polarities and everything. That's where it's all coming back to these routers. These routers, there's 3 routers, there's 3 different zones in this vivarium for the actual count of all your BACnet devices. We had to separate it down to 3 controllers. These all go through Ethernet, and Johnson Controls is connected into here as well. These are the main brains. They're all divided down. We have a sheet that lists, it's router 3, 2, and 1. We have sheets that say what devices are all on each router, so you'll know which corridors. Yeah, so in there it should say which Phoenix valves will be on this router, which one will be on there, and that's where all the code is written into there to tell the corridor valves to increase or decrease depending on if they go positive or negative. And then that ties into Johnson Controls as well. So this is pretty much the only Delta routers in this vivarium here. It's all right here in this location as you first come into the vivarium, so you don't have to go searching through everywhere. And I think that's pretty much it for the Phoenix on our side.
For alarms, those general alarms, that you begin, like what if you have like a bad vape pod or a bad actuator, is that going to be seen on the front end of Johnson Controls, or is that going to, how will that alarm?
If you have a bad actuator, if it's being told to go somewhere other, say it's being told to do 500 and you hit the switch, you want it to go down to 300, if it does not move, the signal goes through here and Johnson's picking it up through, not a hardwire, but actually just through the comm. So they're monitoring alarms, flow alarms, jam alarms.
Okay.
That would be a jam alarm.
That'll come up as a jam.
What we call command feedback mismatch.
Right. And the fume hoods, it'd be a local alarm, and then it should actually go through your Johnson Control system too.
And what's that right there?
These? These are the end-of-line terminators.
Oh, okay.
So when you have so many devices on one comm system, you want an end-of-line. Otherwise, the signal could kind of go out to infinity, and it just slows down the comm. And sometimes you get breaks where sometimes a device will pop up, and then it'll go off, it'll pop up, it'll go off. This just kind of completes the circuit, says, hey, this is where I'm ending, just go to here to look and stop. Because it is MSTP, the master-slave token passing, it'll just keep going, and if it doesn't see that, it'll try to send it out, and it'll wait for a little bit sometimes, and it's waiting for a response. This here is saying, okay, come to all the devices, stop here, now go back.
Okay.
Stop passing the
Terminator.
token.
Stop passing the token, buddy.
Right. So again, if you don't see any lights in here, problem is going to pretty much be at your transformer panel. You can go pop open one of those.
Let's say one of those goes bad.
One of these routers?
One of these
End of lines?
End of line. Yeah. Has that happened to you? And
I don't think they've ever. There's no real.
Electronics in there.
Yeah, it's mostly resistors and I think capacitors, or I don't think they've ever really
Just
had an end of line
troubleshooting
go down. Unless one of these legs maybe gets bent to where it's broken off. You might see in your comm, you might see some slowing. It would be, you might not see anything at all. If your system's really tight, this could break and it might still keep functioning just like nothing even happened.
Wouldn't notice, maybe.
Right.
Okay.
But they always say that any type of a MSTP system, you always want to put end of lines in. The Johnson Controls has it. Sometimes they have devices that have a built-in end of line. They flip a switch. Sometimes they put in their own end of line wired terminal. Each place usually has its own end of line, and they usually always recommend when they do any troubleshooting, the first thing the place will do that you call up, they'll say, is your wiring good? Do you have end of line terminators on there? If you say no, they'll say, call me back, go put an end of line on all your runs and then call me back. And then, because they could be troubleshooting for days and the issue might just be that. So.
this won't be an issue, but every valve has a directional airflow arrow on it. Maybe the reflection off my, yeah, you see, can you see that white label with the red arrow?
Yep.
So that's you get a white label on a horizontal valve. Of course, the air has to be flowing the right direction. That's important. We check that all out during startup. But when the valves are vertical, the label is a different color. So if we go over to the vertical valves over here, sorry, Mike, man. So these valves are exhaust valves, and I don't know, this one is, can you see that's a yellow label? I don't know if you can see it. You see it right there? It's yellow when the air flows up through the valve. And did you see that, man?
Yeah.
Okay. And then when it's flowing down, oh, this one you can actually see. The label is blue when it's flowing down through the valve. See the label's blue there? So if the air is flowing vertically down, you should see a blue label. Up should be yellow, horizontal should be white. Also, is that yours? Whose was that? I'm sorry. About to give away your tools. Because this is a supply valve, air is actually coming, air enters the valve from this side, and as it leaves the valve, that's where your control arm penetrates the valve body. Then it goes down and into the vivarium. The exhaust, you'll notice your potentiometer is up at the top because air is flowing this way. Air enters at the opposite end of the control arm, goes through the valve. You notice it's got kind of a venturi waste coming in and a conical discharge coming out. That's mainly for acoustics, but air should come into the end where it venturis in quickly and then leaves the part where it conically discharges slowly. So the air doesn't separate as it's flowing through the valve. So this air, you know air is flowing this way because the control arm's at this end. You know air is flowing that way because the control arm's at that end. Is a drawband clamp. When you have a corrosion resistant valve, that might be a hood or a biosafety cabinet. Normally you can attach our valve by just putting Tech screws right through the ductwork and our valve. Our valve slips right inside ductwork, so you just drive a Tech screw a little bit of pookie and you're done. On the exhaust, you don't want to penetrate our phenolic coating. So you use this 2-bolt drawband clamp. You tighten it on the duct, you tighten it on the valve. Valve is slightly smaller than the duct, so it binds here, and then it's got this knuckle in there to bite onto the valve body. So it bites both places without penetrating the coating of the valve.
There's also tape in here too.
And we put some Viton tape underneath for corrosion resistance.